In the previous lesson on memory, we learned about the standard consolidation. And in this view, the hippocampus integrates perceptual information and makes an initial episodic memory, serving as a pointer or index to reinstate a weak cortical memory. But over time, through the process of consolidation, that cortical memory gets stronger, such that the link to the hippocampal memory is no longer necessary for retrieval. But critically, for the standard consolidation theory, the idea was that these were identical memories. The hippocampal memory and the cortical memory were identical memories. It's just that in a sense, their location had moved. Now, that was standard consolidation theory. However, in time, some researchers began to question the accuracy of this model. And they went back to the original data with HM. So yes, it was true that HM and others with similar damage, so we're talking about removal of hippocampus and surrounding tissue bilaterally, yes, HM and others could produce memories of their childhood, but, and this is a big but, those memories were schematic and lacking detail and vividness. So they could remember, notice the quotes here, they could remember that a birthday party involved cake and party games, but the detail of the episode was lost. It's as if they were not able to relive it the way a neurologically intact person would. So perceptual, temporal, and contextual information was absent. Remote episodic memories were different when the hippocampus was damaged. They resembled semantic memories. And so was born the trace transformation theory, that perhaps the hippocampus was still required in order to retrieve these detailed, rich, contextually specific episodic memories. So in trace transformation theory, those links between the hippocampus and the cortex remain necessary for retrieving context and detail-rich episodic memory. So you'll recall in the standard consolidation theory, once consolidation occurs and the cortical memory is strong, we no longer need the hippocampus to retrieve that memory. In the trace transformation theory, those hippocampal links are still required if you're going to retrieve a very rich and vivid episodic memory, like you're able to relive the episode. So for trace transformation, the consolidation process is a process whereby a memory is transformed from a detail-rich and context-specific memory into a more generalized version of the memory that can be integrated with other stored information in the cortex. The memory becomes more schematic, but hippocampus independent. Notice then in this description, we're almost talking about that very transformation between episodic memory into semantic memory. And let's take a look at that gradient of recall then. The gradient reflects the time course of memory transformation, where episodic memories lose details and become more schematic or semanticized, to coin a new word. More remote memories have gone through this transformation, so the cortical representation of remote memories contains general features, the gist of the event, that are independent of context. So for example, HM and others might remember a certain birthday, that it has games and cake and so on, but they're not reliving it. They have a semantic version of their episodic memory. The hippocampus is required for recreating the detailed and vivid context of an event, so it can be recollected, no matter how long ago the memory was acquired. Therefore, without a hippocampus, recent memories cannot be recreated and there is no cortical representation of the gist of the episode. For remote memories, all that can be retrieved are schematic versions of personal memories. So what is it that is happening during this memory transformation? Well, let's look on the left part of the diagram. Let's suppose we have some kind of episode that the hippocampus made an episodic memory and the episode was happening in context A. Now initially there was some weak cortical representation of that memory as well. And then we go through consolidations so that over time the cortical memory gets stronger. But if we were to retrieve that episodic memory, most likely we would be doing so in a different context than the one that the episode actually happened in. So if I go to the zoo, that's context A. Now, the next day or next week, if I remember my time at the zoo, that's a different context. I'm probably retrieving it in my living room. And so the idea is when you reactivate the episodic memory in a different context, there will be different hippocampal representations involved because it's a different context. Nevertheless, you're reactivating the cortical representation for the episode. And so maybe what the brain is doing is it's extracting the common elements of each reactivation of the memory. And that becomes a more generalized version of the memory, a more semanticized memory, a more schematic memory of the zoo experience, for example. So, the reactivation of a memory often occurs in new contexts, so that new hippocampal memory traces will be bound to the cortical trace. The multiple hippocampal traces will share most or all of the information about the initial experience. During consolidation, common features of the multiple memory traces are extracted to form a more general representation of the gist of the experience. The precise perceptual and contextual details are lost. The cortical memory trace is a more semantic version of the experience that can be integrated into a larger body of semantic knowledge about the person's history. So, in this scenario, the zoo experience is getting transformed over time. As I recall and retrieve that zoo memory, what may be happening is that over time I'm going to be storing a semantic version of that memory, and I might lose the particular details, the vividness of that zoo experience. Yet I'll still have a version, a more semanticized version of the zoo experience in my cortical memory system. Now, under trace transformation theory, it's not that these two memories are mutually exclusive. They can coexist. So we can have access to the detail and vivid episodic memory. I can still retrieve that, what it felt like to be at the zoo, but I can also, under other circumstances, sort of just retrieve a more generalized episodic memory of that event. However, if the hippocampus is lost, under trace transformation theory, then the cortical gist-like version of the memory is all that can be retrieved. And so again, when researchers went back to sort of look at how H.M. described his own episodic memories from his past, they noticed that he didn't seem to be retrieving all that detail and that rich context-specific stuff. He wasn't reliving them like intact folks would do. And so the suggestion was that he was retrieving a more semantic version of his past. He had lost the ability to retrieve detail, context-specific, vivid episodic memories of his past. In the intact brain, the demands of memory retrieval may dictate which version is activated. If only abstracted, gist-like information is needed, the cortical memory will suffice. If detailed and context-rich information is needed, the hippocampus must be engaged. In other words, if somebody said, take yourself back and relive that episode, then the idea is you need to reactivate the hippocampal memory system as well. If somebody just said, well, what did you learn from your trip to the zoo, then you're maybe just accessing the semantic version of the memory. Using our other diagram, the difference between knowing and remembering, it's as if H.M. might know about his past. He might have semantic information about his past, about himself in the past, but he lacks the ability to retrieve the vivid, detail, context-specific episodic memories because he's lost his hippocampus and surrounding tissue. And so on this view, then, the hippocampus and the surrounding tissue is needed for the vivid, detailed, context-specific recollections. For patients who have lost this memory system, the only thing that remains is a semanticized memory for their lives.